Okay, welcome back. 3.3 product rule, quotient rule. Okay, so recall there's all these rules that kind of already exist that we work with. Things like 25, or how does this work? 16 plus 9, is that the one? Yeah, all right, so this guy, 16 plus, square root of 16 plus 9. And hopefully you don't think that's equal to the square root of 16 plus the square root of 9. This would be not true. It's not equal to 4 plus 3, which is 7. No, clearly if you were to add 16 plus 9 in there, you get square root 25, which is 5. Okay. So this is definitely not going to work for us. But there were rules that did work, right? So the square root of 16 times the, no, let's find the one that works, right? So the square root of, I don't know, 15 times the, what am I even trying to do here? I guess I didn't think this through very much. So the square root of, square root of something. Let's say, I don't know, 36a squared, okay, where a is positive. So you could split this up in the square root of 36 times the square root of a. And then you could say, well, that's square root of a squared is 6a. Right, is your answer. So what I'm getting at is sometimes you can use rules to kind of, all right, I can't break these apart, but I can here. Okay, basically the square root of a sum is not equal to the sum of the square roots. Here, the square root of a product is equal to the product of the square roots. Okay, so we have all these rules, and we've kind of already started encountering these rules with derivatives. Okay, so now we're dealing with all these weird rules for derivatives. In particular, we saw the derivative of a sum. So maybe the derivative of x squared plus sine of x minus e to the x, we can find by taking the derivative of the parts. Now this is completely different than this idea, right? The square root of a sum is not equal to the sum of the square roots. But here, the derivative of a sum is equal to the derivative, the sum of the derivatives. Okay, so it's just equal to the derivative with respect to x squared plus the derivative with respect to x of sine x minus the derivative with respect to x of e to the x. Okay, certainly that's equal to 2x. What's the derivative of sine? Well, that's cosine. And then the derivative of e to the x, it's always e to the x, right? Okay. So here it's different than the radical. So maybe we ask ourselves, is the derivative of a product? So maybe the derivative of x squared times cosine x, is that going to be the product of the derivatives, like the square root of a product is equal to the product of the square roots, right? So we wonder, is this equal to the derivative with respect to x of x squared times the derivative with respect to x of cosine x? And it turns out in general, no, that's not going to be the case. Okay? So what the heck is the derivative of a product? You know, what do we got to do? Can we even do it, right? Over here in square root land, you know, I have no idea how to split them. Is there a clever way that could kind of split it up? And it turns out there is. Okay? There is a way to get the derivative of a product. This is not the way. Okay? This is not going to work. It will work in certain crazy circumstances, but it's a freshman dream to think that would actually pan out. Anyways, let's go ahead and take a look at the proof of this thing. Okay. Figure out a formula, and you do it via limits, right? So the derivative of a product of two functions. So we'll use the limit definition to finagle this answer. So we have f of x plus change in x times g of x plus change in x minus f of x times g of x all over change in x. Okay. The gate to opening up this problem, the gateway for opening up this problem, is to immediately add and subtract in a special term that will allow us to kind of exploit the fact that each one of these supposedly has a derivative. I believe that's probably one of the criteria for being able to take the derivative, is that each individual has a derivative. Okay. So what is that special value? I'm going to add and then immediately subtract. Let's see, f of x plus change in x times g of x plus change in x. It's got to be something that will allow us to split it up into two parts. And it turns out to be this, f of x plus change in x times g of x. So we add that in, or subtract it, and then we immediately add it. And then we still have the minus f of x, g of x, part all over change in x. Then this will equal, now we want to split it up into two parts. The limit as change in x goes to 0 of, I kind of want to do it in an appropriate way. Let's see if I can pull this off correctly. So that one portion will be the derivative of g, and one portion will be the derivative of f. So I'm looking for limit definitions of those derivatives encoded in here somewhere. So I think if we just sort of bifurcate it or butterfly it like that, and then like this, we'll be good to go. Okay, and we'll take a limit of each part. So in this first portion, if I factor out the f of x plus change in x on top of everything else that's going on, I'll have that times, I put that over 1 just to make it look all nice like. This times the leftover bits would be g of x plus change in x minus g of x all over change in x. And you see what you're getting is that difference quotient. Okay, so I'll be able to replace this portion with the derivative of g of x. And then over here, what do I want to factor out? I want to factor out the g of x's, because then I'd be left with the difference quotient version of the difference quotient for f of x. Okay, so this then would be plus the limit as change in x goes to 0 of, and this time I factor out g of x all over 1 times f of x plus change in x, oops, that there, minus f of x all over change in x. And then hopefully you agree with me, this portion is just going to end up being the derivative of f of x. Right? So anyways, the limit as change in x goes to 0 of this thing, if you plug 0 in for change in x, you just get f of x. Okay? And then this part of it is just the derivative of g of x. And then over here we have g of x. And then this portion is a derivative of f of x. Okay, so it's some real awesomeness that we have a formula. It's not, it's not f prime of x times g prime of x, which would have been nice, but at least we have something. Okay, we have something that allows us to get our hands on an answer. Okay, so let's apply this, right? This formula. We have y equals 3x minus 4 times x cubed plus 5. And before, we would probably FOIL it all out and then go term by term, right? And now we can use this formula. So let's let this guy be f of x, and let this guy be g of x. Okay, so y prime, you kind of think of it as leave this guy alone. Okay, so you have 3x minus 4. And then take the derivative of this part. So the derivative of x cubed, bring down the 3. X to the 3 minus 1 is 2. Derivative of 5 is 0. Plus, now I leave this guy alone and take the derivative of this guy. So the derivative of this guy is just 3, and then leave the g of x alone. And then it's a matter of simplifying, right? So distribute, so I get 9x cubed minus 12x squared plus 3x cubed plus 15. Combine like terms, so 9, 10, 11, 12x cubed minus 12x squared, and then plus 15. Okay, and there it is. There's our derivative. Yay! Yeah, everybody rejoices. Let's look at a couple more. Get some more practice here. Here's number 4. We have some g of s function equaling square root of s times s squared plus 8. You can go ahead and distribute, but we want to get practice with the product rule. So you're not going to be able to always just distribute or FOIL or something like that, right? Okay, in order to pull out the product rule, I want to rewrite this square root of s as s to the 1/2, and then go from there. Okay, so g prime of s, leave the s to the 1/2 alone, and then times the derivative of this. So the derivative of s squared is 2s. The derivative of 8 is 0, so I'll leave that there. And then plus, now you take the derivative of this part and leave this guy alone, right? So the derivative of s to the 1/2 will be 1/2 s to the negative 1/2. And then I leave the s squared plus 8 alone. Okay, you got a bit of cleaning up to do with this one. That's the drawback here. You can multiply out these exponents, right? So you get s to the 1/2 times s to the 1, which is s to the 3/2. So I got 2s to the 3/2. And then this guy, if I rewrite it a bit, it'll be 1 all over 2 square root s times s squared plus 8, if you wish. And I don't know, I think that's good enough. You leave it like that. Okay. All right, so number 17, this is definitely one where you couldn't sort of distribute and use power rules. And these past ones, I didn't really need the product rule. This guy, you need, absolutely, positively need the product rule. Okay? So y prime, leave x alone, take the derivative of cosine. Derivative of cosine is negative sine. Plus, this time, take the derivative of x, which is 1, and leave cosine alone. Okay, clean it up. So I get negative x sine x plus cosine x. And that'll do it for now. Let's move on to the quotient rule. And it looks like this. So the derivative of f of x divided by g of x is, and they have kind of a little, I don't know, rhyme that goes with it. It's low d high minus high d low. Low, g of x, times the derivative of the high minus high times the derivative of the low. Okay. And then it's all over the low guy squared. You'll need this rule. You can, honestly, you can get around ever having to use it by just rewriting everything in terms of negative exponents with this denominator. But this is better. Okay? It'll make your life a little easier if you learn this rule, learn it now, get it out of the way, and you won't have to suffer later on in life like I did. Okay. Okay. So, anyways, let's take a look at it. So here's number 8. G of t is 3t squared minus 1 all over 2t plus 5. Right. Okay, so g prime of t, low times the derivative of the high, so I have 2t minus 5 times the derivative of the high. So the derivative of this, bring down the 2, I get 6t to the 2 minus 1 is 1. Derivative of 1 is 0. Minus high is 3t squared minus 1 times the derivative of the low. So the derivative of 2t is 2, and the derivative of 5 is 0. And then that's all over the low squared. Okay, then we need to clean this up. So distribute. So I have 12t squared minus 30t. Distribute here. Okay, and I'm distributing this negative 2 at the same time. So it's really negative 2 times 3t squared is negative 6t squared. Negative 2 times negative 1 is plus 2. Combine like terms. So 12t squared minus 6t squared is 6t squared. Negative 30t then. And then plus 2. Okay, well, it looks like as far as we can go with that. It's not going to simplify any further, so we'll leave it there. Okay, let's look at another. This is 18, and we have f of x is sine of x over x. So f prime of x, low d high, low times the derivative of the high. So leave the low alone. Derivative of high is cosine, minus high, leave that alone, times the derivative of x is just 1, all over the low squared. Not much to do there. This is x cosine x minus sine x all over x squared. How's it? Okay, let's look at maybe some nastier ones. 29, I have x times, or sorry, my function, f of x, is x times 1 minus 4 over x plus 3. In order to pull this off, I'm just going to rewrite it as one fraction and then do a quotient rule on it. Okay? So inside the guts, this I need a common denominator between these, so I go x plus 3 all over x plus 3. So you'll have x times x plus 3 minus 4. X plus 3 minus 4 is x minus 1 all over x plus 3. And then I'm going to distribute in this x. So x is the same as x over 1. So if you multiply straight across, you get x squared minus x all over x plus 3. Okay, so now I can do a quotient rule, f prime of x. And I mean, if you wanted to do long division and then take the derivative of the result, you could do that too. I'm just going to use quotient rule though. That seems easier. So low x plus 3 times the derivative of the high. So the derivative of this, bring down the 2, you get 2x to the first power, minus the derivative of x is 1, minus high times x squared minus x, is x squared minus x, times the derivative of the low, which is just 1. And then that's all over x plus 3. Okay, I can FOIL these characters out. So I get 2x squared plus 6x minus 1x is plus 5x, and then minus 3, and then minus x squared plus x, all over x plus 3. Two x squared minus x is 1x squares. 5x plus x is 6x, and then minus 3, and then that's all over x plus 3. Let's go through two more of these, I suppose. There's 49. Y equals 3 times 1 minus sine of 2x, or sine of x, sorry, all over 2 cosine x. You can do a constant multiple rule here. You can kind of factor out the 3 halves if you wanted to, and then just do a quotient rule on the leftover bits. If you'd rather, you can distribute the 3, though. 3 minus 3 sine x all over 2 cosine x, and then just work with that. That's what I'll do. So y prime is low d high, so 2 cosine x times the derivative of the high. The derivative of 3 is 0. The derivative of minus 3 sine x is minus 3 cosine x. Low d high. Minus high, so minus 3 minus 3 sine x times the derivative of the low. Leave the 2 alone and take the derivative of cosine, which is negative sine. All over the low squared. Okay, so up top, what do we get? Negative 6 cosine squared. And then over here we have a pretty big mess. This negative times this negative here will be positive 2 sine x. 2 sine x times 3 is 6 sine x. 2 sine x times 3 sine x is 6 sine squared x. And then that'll be all over 2 cosine x squared. Did I screw up the signs here? Yeah, this would be minus, so this would, sorry, this would be minus 6 sine squared. You can simplify a little bit, and you want to get used to using these trig identities to simplify. The most important trig identity we have, sine squared x plus cosine squared x is 1. And this identity is in here. It's kind of hidden. But we can rewrite, right? You can factor out a negative 6 from this guy and this guy, and you get sine squared x plus cosine squared x. And then plus 6 sine x all over 4 cosine squared x. Okay. And then that'll equal negative 6 plus 6 sine x. Right. Sine squared plus cosine squared is 1. Negative 6 plus 6 sine x all over 4 cosine squared. I don't think there's much you could do here. You could, I guess, factor out the 6. I get 6 times sine x minus 1 all over 4 cosine squared x. And then 6 over 4 is the same as 3 over 2. So maybe, I don't know, 3 sine x minus 1 all over 2 cosine squared x. That's good enough. Okay, let's now, so one of the issues with this quotient rule is people will try to apply it when it's really not what they're supposed to do. They're kind of using a nuclear bomb to hammer in a nail, right? So it looks like you should be using the quotient rule, but not really. It's just a constant multiple rule. All right, so number 22, y equals 5x squared minus 3 all over 4. Okay, so some people want to go and do low d high minus high d low on this thing, right? Low d high, no, that's wrong. You're not supposed to do that. This is just 2 fractions. So it's 5 fourths x squared minus 3 fourths. And then you're going to do a power rule, and the derivative of that guy is just 0. So y prime is, bring down the 2, so you have 5 fourths times 2x to the first, and then the derivative of 3 fourths is 0. Okay, so you'd end up with 5 halves x. Let's get another one, 25. Y equals 4x to the 3 halves all over x. Okay, so here you can use some of your rules of exponents to simplify. And that's just 4x to the 3 halves minus 1, which is 3 halves minus 2 halves, which is 1 half. And then you do the derivative. So y prime is 4 times 1 half x to the 1 half minus 1, which is negative 1 half. 4 times 1 half, of course, is 2 times x to the negative 1 half. And then you could bring this down into the denominator, 2 over x to the 1 half. In other words, 2 over root x. Okay. Okay, just a couple extra things. Once you get the quotient rule, you can do the derivatives of the rest of your trig functions. And these are super important. Any calc student worth his weight in nickels should be able to find the derivatives of all the trig functions. Okay. And we wait until now to give you the rest because you need the quotient rule. It's easier to use the quotient rule than the limit definition to prove these derivatives. So in particular, we have this kind of table, and we want to know the derivatives of all 6 of our standard trig functions. Oops. So tangent. Okay, so we already know these two. The derivative of sine is cosine. The derivative of cosine is negative sine. Okay, but these other ones we don't know. So let me fill them in now. Oops. So the derivative of tan is secant squared. Derivative of cosecant will be negative cosecant, cotan. Derivative of secant is secant x, tan x. And then the derivative of cotan is cosecant, and it's negative cosecant squared x. Okay, so hopefully you note the pattern of the negatives. It's like these guys are negative, and the other ones are positive. You need to have this memorized. It should be automatic. Okay? So memorize. Say them over and over in your head. Write them out 100 times before you go to bed. Whatever it takes to make them automatic, so that they are not going to go away. You'll see them again and again and again. In one form or another, you need to have them encoded into your brain. Okay? Okay, so anyways, if you use the quotient rule, you can show these things. In particular, let's try the tangent. So the derivative with respect to x of tan x. So why is that secant squared? Well, you can rewrite it as a difference of the derivative of a quotient, right? So the derivative of tan is the derivative of sine x all over cosine x. And then it's low d high minus high d low. So low times the derivative of the high minus high times the derivative of the low, all over the low squared. Right, then cosine is cosine squared. Sorry, so low d high minus high d low, the derivative of the low. In that case, the derivative of cosine is negative sine. Sorry. Okay, so cosine is cosine squared minus sine times minus sine is plus sine squared, and that's all over cosine squared. Cosine, that's Pythagorean identity right there. 1 is equal to 1. It's 1 all over cosine squared. And then sure enough, 1 over cosine, if you remember, is secant. So it's secant squared x, which is what we wanted to show. Okay, so like I said, memorize those guys, know them, back your hand. Let's look at least one problem from the book. Here's number 40. y equals e to the x minus cotan x. The derivative of e to the x is just e to the x minus the derivative of cotan, we said, is negative cosecant squared x. So this is equal to e to the x plus cosecant squared x. Flashcards are a miracle here when we start getting more and more stuff. So you can do flashcards for the trig derivatives, include the exponential derivative in there. They probably have them online, so you could do it with your cell phone while you're bored. Okay. The last part then, finding higher order derivatives. This can be kind of tedious, but it's important for later on when we're doing what are called Maclaurin and Taylor series, right? Or Taylor polynomials and Maclaurin polynomials as well. So we're going to need to be able to do this, and it just means taking the derivative over and over. Okay, so there's problem 101. We want to find the second derivative, and one way we can notate that is y double prime, or y2, like that. So anyways, 101, y equals x all over x minus 1. So I can do quotient rule for my first derivative. Low d high, x minus 1 times the derivative of the high is 1, minus high times the derivative of the low. The derivative of x is 1, the derivative of negative 1 is 0. All over the low squared. Simplify, so I have x minus 1 minus x over x minus 1 squared. Then that'll be minus 1 over x minus 1 squared. Y double prime. So you may think, ooh, I want to do a quotient rule on this. No, don't. Okay. You could rewrite this thing as negative x minus 2, or sorry, yeah. It's equal to negative 1 times x minus 1 to the negative 2. So what we're going to do is use the power rule on this thing. Okay? And we'll have to, later on, there's something called the chain rule, but it won't really affect us here because of this type of binomial. Okay, so what is he talking about? What we're going to do is just pretend this is variable x instead of x minus 1 and bring down the exponent. So it'll be negative 1 times negative 2 times x minus 1 to the negative 3. So subtract 1 from negative 2 to get negative 3. And that'll be 1 all over x minus 1 cubed. Okay, so what's coming up then is the chain rule. When am I allowed to kind of deal with a function like this as it's like it's just a variable or something like that? So if you didn't catch what I did, it's like what's the difference between the derivative of this and the derivative of this? Okay, how do these work? Well, the derivative of the first guy, we can rewrite this using exponent. So this is negative x to the negative 2. Its derivative, then, y prime, leave the negative out there by itself, and then take the derivative of this. So that'll be negative 2x to the negative 2 minus 1 is negative 3. So that'll equal negative is positive 2x to the negative 3, and then drop the negative 3 exponent downstairs. Okay. For the other guy, what I'm saying is we need kind of a rule for when can I attack this and this in the same way. And it's going to be the chain rule. In this section, you can just simply not worry too much about it. Right? So I can rewrite this guy as x minus 1 to the negative 2, and then do a power rule to get my answer. So bring down the negative 2, negative 1 times negative 2 again is, we can write it out in all of its glory if you wish. It's going to be that. And then y prime, that when I simplify, will be positive 2 times x minus 1 to the negative 3. And that'll be equal to 2 all over x minus 1 cubed. Okay, so hopefully you can kind of see what the issue is here. They're exactly the same derivative, except one has x in the denominator, one has x minus 1 in the denominator. And the deal will be is that's not always going to work. It'd be cool if it did, but it won't. And we'll have the chain rule. In this case, it works, but in general, you'll have to have a chain rule, and you have to kind of tack on the derivative of the guts, the function that you're allowing to equal x, whatever this thing is. The derivative of x minus 1 is just 1, so there's not an issue. Okay, so that's next time. Thanks for watching. Bye.